Hi, and welcome to the Lost Landscape. Today, we're breaking down every major way to fine-tune a large language model, full fine-tuning, LoRA, QLoRA, SFT, and DPO, using one simple example with no scary math. When we fine-tune an AI model, do we change all of its billions of weights or just a tiny sliver? In the next 10 minutes, you'll understand every major fine-tuning method. Full fine-tuning, LoRA, QLoRA, SFT, DPO, and more, using one simple example and no scary math. We download a general model. It knows English, coding, and science. But we want a support assistant for our store, EasyShop. A customer asks, "My order is late. Where is it?" The general model says, "Contact customer support." Correct, but useless. What we want is, "I'm sorry your order is delayed. Please share your order ID and I'll check its status." It already knows English. We only need to teach it our format, our tone, and what to ask. That teaching is fine-tuning. Picture the model as billions of tiny knobs called weights. A 7 billion parameter model has 7 billion of them. We show it an input and the correct reply, measure how wrong it was, the loss, and nudge some knobs. One knob barely moves the needle, but adjust millions of them across thousands of examples, and the behavior we want appears. Every method we'll see differs in one thing: which knobs we turn and how many. Here's the idea that clears up all the confusion. There are two separate questions. One, what are we teaching? Two, how are we updating the model? So SFT and LoRA are not rivals. SFT is the data and the goal. LoRA is which weights change. You can run SFT with full fine-tuning, with LoRA, or with QLoRA. Keep these two apart and everything else falls into place. First, what are we teaching? If the model has never really seen medical, legal, or your internal jargon, we feed it a large pile of raw domain text and keep its next word training going. That's continued pre-training. Use it to soak up a domain's language, not to teach a reply format and expect to need a lot of text. Most of the time, you want supervised fine-tuning. You give correct input and output pairs, and the model learns to make the right reply more likely. Many varied instructions, and we call it instruction tuning. It's how you teach formats, tone, JSON output, and tool calls. In practice, a few lines with hugging faces, SFT trainer. Sometimes both replies are fine, but one is better. Preference tuning teaches the model which one people prefer. The classic way, RLHF, trains a reward model and uses reinforcement learning. DPO, direct preference optimization, skips the reward model and trains straight on preferred versus rejected pairs. Use SFT to teach a good answer. Use DPO to pick the better of two. Now, how do we update the weights? Full fine-tuning lets every weight change, 100% of them. Maximum flexibility. But for a 7 billion model, mixed precision training needs roughly 18 bytes per parameter. 7 billion times 18 is 126 gigabytes before activations. That means multiple big GPUs. A rough experiment: 4 GPUs, 8 hours, $3 an hour, $96, and you'll run many. Use it when you have the compute, the data, and the smaller methods just aren't enough. Cheaper: freeze most of the model and train only the last few layers, say the final 4 of 32. Less flexible, since the early layers can't adapt, but fine for simpler tasks. These days, LoRA is usually the more modular choice. BitFit goes further. Freeze the big matrices and train only the tiny bias values. Usually well under 1% of the model, full fine-tuning rebuilds the whole machine. BitFit just tweaks its alignment screws. Cheap but limited capacity. Adapters insert small new blocks between the frozen layers and train only those. One base model, many specializations. A medical adapter, a legal one, a support one, swapped in as needed. The classic study reached near full fine-tuning quality, adding about 3.5% parameters per task. Prompt tuning doesn't touch the model at all. It learns a handful of invisible virtual tokens. Trainable vectors slipped in front of every request. With hidden size 4,020 tokens, that's about 80,000 parameters. around 1,000%. Prefix tuning is similar, but reaches deeper into the layers. Both are tiny and cheap, but weaker for big behavior changes. LoRA is the one you'll reach for most. Instead of editing a giant weight matrix, it freezes it and learns the change as two thin matrices. A times B. The idea, the update it needs is simpler than it looks, so a low-rank shortcut captures it. That rank, controls capacity. For a typical 7 billion model, adding LoRA to the query and value projections trains about 8.4 million parameters, roughly 0.1%. The original paper reported up to 10,000 times fewer trainable parameters. Good quality, small footprint, and a separate lightweight adapter for each customer. QLoRA squeezes further. First, freeze the base model and compress it to 4-bit. 7 billion weights at 16 bits is about 14 gigabytes. At 4 bits, about 3.5. Then train small LoRA adapters on top. The QLoRA paper fine-tuned a 65 billion model on a single 48 gigabyte GPU. It uses less memory than plain LoRA, though it can be a bit slower. Reach for it when the model just won't fit in normal memory. So, which do you pick? Try prompting first. If a clearer instruction works, train nothing. Need fresh facts, prices, or docs? Use RAG. Need a tiny tweak? Prompt or prefix tuning. For most real work, formats, tone, tools, domain, use LoRA. Tight on GPU? QLoRA. Lots of compute and need deep change? Full fine-tuning. And once it answers well, but you want it kinder or safer, DPO after SFT. One warning, more training isn't always better. A narrow style might need 1,000 great examples. Strong behavior, tens of thousands. Start with one epoch, check your validation, and keep going only if it improves. 10,000 clean examples beat 100,000 messy ones. Fine-tuning learns your data's patterns, mistakes, and all. So, the whole picture. SFT, continued pre-training, and DPO describe what the model learns. Full adapters, prompt tuning, LoRA and QLoRA describe how its weights update. Full changes everything. BitFit just biases. Adapters add blocks. Prompt tuning learns tokens. LoRA learns a small low-rank update. QLoRA does that on a 4-bit base. Here's the cheat sheet. Every method, what it trains, and its main benefit. Screenshot this one. For most people starting out, LoRA or QLoRA with supervised instruction data is the sweet spot. Thanks for watching. If this made fine-tuning click, subscribe to The Lost Landscape for a new explainer every week, and I'll see you in the next one.